right, so here we go. We're on lesson 13. We're going to be dealing with polynomial functions. We're not going to go too much into polynomial functions right now. We'll do some more of that later, but for now, we're going to talk about what a polynomial is and a few things about them. So we'll talk about that a little bit. So let's go to our first example, which is we're going to talk about what a polynomial is. Okay, and so a polynomial is a function that can be written in this form. And this is a very, I guess, a technical looking definition here. And I would rather you know what it means practically than, how to do this exactly, right? To really dissect it. So what this is saying is that you have x to some power, right? That could be a 5, a 4, a 10, okay? But it's going to be a natural number. So that means it's going to be a positive whole number. And it's going to have a coefficient in the front, okay? A coefficient, so a number in the front of it. It could be a fraction, could be a whole number, could be positive, negative, square root, doesn't matter, okay? And so you have each of these individual terms, which is made up by a coefficient, a variable, and its exponent. And then you have multiple of the same, or multiple terms, okay? And they don't have to all be the same thing, of course, right? You can have something like f of x equals a coefficient of 1/2 x to the 4th power, that could be a term, plus 3.2 x to the 2nd power plus 5, right? That could be a polynomial here. You have distinct terms, you have exponents that are all natural numbers, positive whole numbers, and you have coefficients on them, right? By the way, if there is no coefficient, of course, you know this by now, that's an understood 1 in the front there. Okay, so understood coefficient of 1. All right, so this is just an example of a polynomial function. Some things to know about these functions, though, is that their domain is always, at least the implied domain, is always going to be negative infinity to positive infinity. Okay, that's just kind of how it's going to work, the domain, no matter what. And if you look at the graphs of them, you can see that it's always going to go forever to the left and forever to the right. Remember, typically what happens when we have a problem with the domain is that you're dividing by 0 somewhere, right? Potentially dividing by 0. Or you have a negative under a square root or a 4th root or something like that. But if you look back at this example here, notice there are no fractions, so there's no x in the denominators anywhere. So there's no potential for dividing by 0, nor are there any radicals, right? So you don't have to worry about that either. Okay, so we should be good there. Now, as far as the range, well, that just kind of depends on the graph, and it really depends on the degree. So the degree, by the way, the degree is the highest exponent. Okay, so if I'm looking at the highest exponent, and I see that that exponent is an odd number, then the domain, I'm sorry, the range will be either some number, or I'm sorry, negative infinity to positive infinity. Negative infinity to positive infinity. Okay, because it has some sort of graph like this. All right, that's an odd degree polynomial. It goes down forever, it goes up forever. An even degree polynomial, they're usually shaped something like this, either like that or like that, right? And so there's an obvious cutoff point, and then it goes up forever, or there's a cutoff point and it goes down forever. Okay, so it can be one or the other. So the even degree, you either are going to have some number to infinity, right? If it looks like this, or you're going to have negative infinity up till some number if it looks like this, okay? So it kind of depends on the shape of the graph, and we'll talk about that towards the end here today. All right, so domain's easy though, right? Negative infinity to positive infinity. All right, so now we talked about what a polynomial function looks like, what it is. Now let's identify whether or not these are polynomial functions or not. Okay, so first of all, this one right here, this f of x equals 6x cubed minus 7x squared plus 1. What I'm looking for are individual terms exponents are positive whole numbers, right? Natural numbers. It meets that definition. So this one is a polynomial. Okay. For this one here, individual terms, positive whole number here. Oh, that's x to the 1/2 power, right? When you see a square root, that just means x to the 1/2 power. That 1/2 power there, of course, is not a natural number. So this one is not a polynomial. Okay, here, looking at 3 terms, I see a negative exponent, not a positive number. So this is going to be not a polynomial. It's going to say no. Okay, D is a tricky one. X to the 3rd times x plus 1 plus x. Okay, so that one's, it looks like it's factored out. So I don't see individual terms, but I can imagine if I distribute that x to the 3rd power, I would get x to the 4th power plus x to the 3rd power plus x, right? So that's very much a polynomial, right? So yes, that's a polynomial. I just had to do a little work to see it. Okay. This is not a polynomial. This is a rational function, right? It's a fraction. We're not looking at individual terms. So this is just an obvious no. Same is true for this one right here. You have an exponent that's 1/2. So no, not a polynomial. Okay. So we can identify them. Now let's talk about finding the roots. Remember, the word root also means 0. Find the zeros. Okay, so it just depends on what book you're using or who you're asking. And this is a complicated problem. It's actually more complicated than the intent of this particular lesson as far as doing it by hand, right? So I actually never intended to do this by hand. So that's why you'll see that I have this Desmos calculator pulled up. And this function I have right here, already typed it in. And it looks like this. All right, zoom out so you can see a little bit better. It's down and it goes up and then down and up and down, and it finally goes up to finish it off. Okay, now to find the roots, remember there's a high correlation or there's a relationship between the x-intercepts and the roots. So one thing to know about a polynomial is that highest exponent, right? The degree tells you the number of roots you should be able to identify. That 5 tells you how many roots there should be. Well, here I found 5 x-intercepts. So there's my 5 roots. It just so happens that they're all real numbers. Negative 3.5. I'm gonna write this down. Negative 3.5. Negative 3. Positive 0.5. 2. And 5. Those are my roots. All right, let's build on that in a second. Let's talk about the factor theorem. So there, again, there's a little bit more to the factor theorem, but this is the most important part that you need to take away. If you have a function that equals 0 at a particular value, right? And so that's our x-intercepts we just identified. If there's a particular value where the function equals 0, if you identify a root, then x minus c, x minus that number, that root, is a factor. So you can factor it out based on that information. Okay, so what does that look like here? Here's our example again. These are the roots we identified. Okay, notice this is negative 3.5 and this is 0.5, right? So we got it there. Okay, and if I wanted to now think about factoring this, because I found the roots, the factor theorem says that x minus that individual root is a factor. Okay, that's gonna be plus 3, of course. x minus 7/2 is a factor. I'm sorry, negative 7/2. So again, that's going to make a plus. X minus 1/2 is a factor. X minus 2 is a factor. X minus 5 is a factor. Okay, so those are 5 of the factors. Now, if you want to really pay attention here, and I want to factor this function here, which is what I'm trying to do. If I were to multiply out this times this times this times this times this, right? If I multiplied that leading term in each set of parentheses, that would give me x to the 5th, which is not quite what I need, right? I need 4x to the 5th. There's a very simple workaround here. Stick a 4 in the front. So now you're multiplying 4 times x times x times x times x times x, which is 4x to the 5th. All right, so there we go. We factored this very complicated looking polynomial function using the roots. It worked out for us. We had real roots, so it worked out nicely there. Okay, so now for a couple of problems, I want to approximate the solution. Okay, I don't want to necessarily find the exact value, so we're going to approximate the solution to maybe 4 decimal places or so. We have these two functions here, f of x equals 3x squared minus 9. And we have that g of x is 4x cubed minus 2x squared plus 1. I want to know, when do these two functions equal each other? Okay, when do they equal each other? All right, so what we're going to do to figure that out is we're just going to graph them. So here's f of x. Here's g of x. Where do they equal each other? When x is negative 1.044. Negative 1.044. Okay, that's our approximate solution here. Okay, all I did was graph them and see where they ran into each other. All right, another method for this, of course, and we mentioned it before, but I do like to talk about it because it's a lot easier to graph sometimes, is to just consider what happens when you subtract things that are equal to each other, right? If I subtracted f of x minus g of x, it would equal 0 if they were equal to each other, right? So what I want to do is actually graph that out. (3x squared minus 9 minus 4x cubed minus 2x squared plus 1. I want to graph this where I'm subtracting them, and I want to see, where does y equal 0? I bet it's going to be at negative 1.044, right? Where the two equal each other. Okay, so here's the graph, and notice, where does this graph equal 0? At negative 1.044. Okay, which again, that is our solution that we found earlier. So 2 ways to look at it. Subtracting them can be very useful. Okay, so graphing is a good tool for estimating this stuff. All right, this is the last, or second to last set of questions here. Okay, here we have a graph of a polynomial function. So we're not told much about this, except this is its graph. And well, we're told it has real coefficients. Use the graph to answer the following questions about f, the function. All local extreme values are shown in the graph. Okay, so they're basically saying that the graph doesn't do anything else. It doesn't go up and then down. You know, it doesn't do anything after the graph. It just goes up forever this way and down forever that way. Okay, so here are my extreme values. All right, what are the questions? The first question is, the function f is decreasing over which interval? Okay, well, remember, decreasing means that if you're tracing it from left to right, you're going down. So here I'm going up. Once I hit this point, I'm now going down. I hit this point, I'm going up again, right? So it was right here, this interval right there. So where is that interval then? Remember, the x value tell you where. And it looks like, and I'm going to round it here. It looks like it's a little bit off center here, but I'll just say it's at 1 whenever x is 1 and x is -2. So it's decreasing from -2 to 1, roughly speaking. Okay, next question. The function f has local maxima at which x values? Okay, well, I only see one. I see one local maximum value, which is here. Remember, it's a local maximum if it's the tallest point in a neighborhood, in the area. So if I'm looking at this square and ignore everything around it, in that square, that red dot is the tallest point. So the local maximum value, or has a local maximum at which x value? When x is -2. Function has a local maxima value when x is -2. Okay, what is the sign of the leading coefficient? Okay. Okay, so a leading coefficient, whenever you're dealing with your polynomial function, is the number attached to the term that has the degree. So for example, if I had something like f of x equals -2x to the third plus x squared minus 4. Okay, let's say that's my polynomial function here. So x to the third, that's my highest exponent, right? So that's my degree is 3. That term contains the leading term, or the leading coefficient. Okay, that's the leading term, and it has the leading coefficient. So the number attached to the x with the highest exponent. All right, so what can I deduce from that? Well, first of all, if the leading coefficient is positive, then the graph goes up to the right. And if the leading coefficient is negative, the graph goes down to the right. Okay, so that's something to keep in mind. So if the leading coefficient is positive, the graph goes up when you look at the right side. If it's negative, it goes down. So looking at the graph here, I'm looking at the right side only. It's going up, right? It is going up to the right. So if it's going up, that means I have a positive leading coefficient. Okay, and the last question here is, what is the smallest degree possible for this function? Okay, so the smallest degree, it's possible that the graph has a higher degree, but what I know for sure is that this graph has 1, 2, 3 x-intercepts. We have 3 x-intercepts. Okay, which means, we said this earlier, that my degree has to be 3. Could be more, and that's if you have imaginary roots, some complex roots, okay? But it has to be at least 3. You look at the number of x-intercepts, that's one way you could tell. Another way you could tell is by looking at the number of turning points this thing has. So let's say, right, or extreme values. So there's 1, there's 2. So the degree would have to be at least 1 more than the number of turning points. So if it goes from going up to going down, that requires, and then up again, that requires at least 3, a degree of 3. All right, and so lastly, let's talk about the end behavior. So we just mentioned this a second ago, but we said if you look at the leading coefficient, you can determine whether or not the graph goes up to the right or down to the right. Okay, so we'll start with that. Looking at the leading coefficient of this one, it's negative, so I know that the graph goes down to the right. Now, end behavior also refers to the left side. Let's talk about that in a second. Okay, this one, I look for the highest degree, it's 8. So this 1.25 is my leading coefficient. It's positive, so I know my graph goes up to the right. This one's a little trickier, but you have to multiply out the 2x, x, x, x to get the leading coefficient here. So 2x times x is 2x squared, times x is 2x cubed, times x is 2x to the fourth. Bumping buttons here. Plus, and then there's some other stuff that goes on after that. Okay, and so that 2x to the fourth is where you're going to find your highest degree. There we have a positive, so we know it goes up to the right. All right, so that tells me about the right side for all of these. Now let's go and let's discuss the left side. The left side is going to depend on the leading the degree itself. Okay, not the leading coefficient, the degree. So the degree here is 5. Remember, the degree is going to be a positive number, a whole number. And those typically will always be even or odd, right? So if the degree is even, then the left side is the same or equals. I like to use the word equals because it reminds me of even. The right side. Okay, it equals the right side. It's not exactly true. It's not doesn't equal, but it does the same thing. So if the degree is even, then you look at the right side. The right side's pointing down, and the left side will also point down. Okay, but that's not the case in this one. This one we have an odd degree. So let's discuss that. An odd degree, the left side at odds with right side. Okay, it's a good little way to remember it. So even, left side equals the right side. The degree is odd, so the left side is at odds with the right side. So that means in this case, that left side is going to go up to the left. Okay, so you look at the right side first. Always look at the right side first. Make that determination. Then look at the degree to determine the left side. Okay, so here we go again on the second one. It goes up to the right. The degree is 8. 8 is even. Even equals left side equals the right side. Going up to the left. Okay, and finally on this last one here, we have degree 4. 4 is even. Even, the left side equals the right side, so it's going to go up as well. All right, and that is lesson 13.